All right, is this on? Yeah. All right. physics time! Woo! Where's the hype? Let's get hyped the F up, because it's time for physics, right? This is the first ever lecture I'm giving that's not starting at 4 p.m., and I'm so excited, for I can finally not have to eat 50 trillion tons of coffee to get here. First of all, welcome everyone. A note, I'm using this new doodad they've got called Echo Poll, right? And it lets you kind of give live responses to questions. And this is kind of gangster. They show up in the PowerPoint like live, right? So there's a bunch of word clouds. No one post bad words, please, but they will go up. The reason the lights are off is because I screwed up and I made all my slides black background. And then I tested these lectures out on a well-lit room, and you can't see shit. And that's, it's important to be able to see stuff. Now, secondly, try not to fall asleep, but that's why I'm also loud, right? One thing I want to talk about for this course, right, is the first few lectures have a lot of different things. If you look at the learning outcomes, you'll see that there's a lot for the early lectures, and there's not too many for the later lectures. Like week 3, for example, the first lecture has like 4 learning outcomes, and it's literally learn how to do this problem, right? So you may look at the number of slides I've got and be like, Tom, how are you going to do all these slides? And the answer is with speed, but I'll show you my system for telling you what you have to pay attention to, okay? But first of all, hi, it's me. That's me in front of my office, and that's fairly emblematic of my vibe. You can email me. You can see me in my office if you want. I wrote all the labs for the course. I'm in charge of all the problem-solving workshops for the course. I did every single assessable problem in this course, so I know everything you can and will be assessed on, and I have written my lectures accordingly, okay? I wrote them specifically so that you can get good marks in your assessment, among some other things. I also run the Equity, Diversity, and Inclusion Committee at the University of New South Wales, oh no, not at the uni, God, I wish, no, at the School of Physics level. So if there's any equity issues that you find during your stay at university, please let me know, because that's part of my job. Next slide. Is it already broken? What's going on? All right, click. Next slide. Okay, whatever. Okay, so is a keyboard not working now? Okay, no. Okay, sometimes the keyboard works, sometimes the keyboard doesn't work. Yay. Look at it go like it's just going by itself now. Okay, we're here. Good? Good. I hate technology, right? So, first things first, my entire job is to teach you, all right? I don't want you to have a question and you not have told me about it, all right? This is my entire whole ass job is to help you through for the first 4 weeks, and then you're on your own. Right, because they've got a different lecturer, okay? So first things first, please join the Discord server. I am terminally online, so I will always answer. I hate doing my job, and so if I can avoid doing my job by helping you out with physics, I will. I'd love to do that. Secondly, I have consult hours if you'd like. I will post these up on Moodle, but you can book them in. In the entire history of me doing this, no student has ever done that, but it is an option, right? We also have problem-solving workshops. You should go to those if you can. We employed some smart people there. And I bet you I have to click next slide now because that's how life is. Okay, so the way learning physics is kind of structured is there's almost like tiers of capability. And yes, I'm doing a lot of meta bullcrap at the start, but it's our first course of the term, and we've got to get into the thinking about learning. So first of all, if you know things, you'd recognize the terms. For example, you'd recognize Gauss's law, and you'd recognize the terms in that, what an electric field stands for, what an integral is, what a dot product is, and you'd be able to describe them. You'd be able to look at a formula sheet and know which formula is which, right? And ideally, by just coming to lectures, you hit that. Then there's the ability to do things, right? Do your standard problems, follow your instructions, right? Make general conclusions from data. I've written the lectures so that you might be at this level just from the lectures. I'd hope, but obviously we can't expect it. We've only got 2 hours a week, 4 hours a week, right? And then there's mastery, which is being able to handle complicated questions that do not match with the circumstances in which you've learned them. Now, I'll be honest, if I do my job right, you will never experience a question like that, because in my lecture, I will have exposed you to all the relevant information to solve any question that comes up in the assessment for this course, because I did all the assessment for the course, right? But ideally, not practically, but ideally, you get to the stage where you have a mastery and you can change things up and deal with problems that aren't the ones that are prescribed. Now, I'm hungry, so I like to think of it in terms of cake, all right? You know what a cake is, and you know what a cake tastes like, right? I want you to know the difference between a carrot cake and a chocolate cake. Those are Gauss's law and, I don't know, some other law in this example. At the level that you must be to pass this course, you have to bake a cake according to a recipe, right? I'll be honest, there's only so many cakes we can ask you about, right? There's only so many questions in the question bank. But if you're a master, you don't need a recipe. You can just raw dog it, right? You can free fall it. You can bake a cake without ingredients. You can make ingredient substitutions. Not without ingredients. That's not how that works. I don't know how to bake, okay? I don't know anything besides physics and maybe Breaking Bad memes. And if I think correctly, this slide is yeah. So ideally, the lectures are going to get you up to part way of the do, right? And if you just come to lectures and then practice the practice problems, you're probably going to do fine in this course, right? Because the accessible items for this course, remember, are the labs, 30%, and those 4 tests you have in weeks 3, 5, 8, and 10. And I've written my lectures to prepare you for those exam questions. And also the labs, because I wrote the labs and I love the labs. But, you know, forgive me for that. The problem-solving workshops will hopefully get you all the way to being able to do damn near every question in the question bank. And the labs and any self-study will get you further. Now, I'd recommend aiming for further, just so if you don't succeed at your goals of knowledge, you at least definitely pass the course, right? Or you slay the course, you do a good job, right? Because that's what we're here for. We're here to kill it, not here to have a mediocre time. So, how can you succeed? Does anyone want to succeed? Yeah? Good. All right. Practice some stuff, okay? The best way to get good at doing the specific things that you're assessed on is to practice the specific things that you're assessed on, which are the quizzes you get every week, right? Those quizzes feed into the exact same question bank that you get in your test. So it is perfect synergy to practice with those and the test. Now, you should also try and engage. I notice we have 23 people here. That is the most people I've ever had in one of my lectures, as you can probably remember, because they always put me on the dog term, right? Like most people do this class in T3, but that's life. And study with your friends, chat with the peeps, right? I don't want to sound arrogant, but it's been a long time since I learned this stuff. And that means I might not grasp the misconceptions that you have. I will try my best, right? I am, after all, pretty good at being dumb. But it might be the case that I can't kind of understand exactly where you're coming from, but your peers will. But most importantly, ask for help, right? You're not in this alone. My entire job is to get you over the line, right? I can't carry you, right? But I will train you. That's my whole job, right? I want you all to pass this course. Now, do we think the keyboard's going to work? Just-in-time teaching is a method of teaching that I like to use. I'm going to send you out a poll before class sometimes. I'm going to ask you what you're still stuck on. I haven't done it this week because, well, there's nothing yet, right? But I want to know, because I like to adapt my lectures, or more specifically, adapt the focus, right? If I, for example, go over how to do an electric field integral, right? To find the electric field due to a rod or something, right? Which is next lesson. And you're like, Tom, how the absolute shit did you do that, right? Then you let me know in the form, because I know no one likes talking in class, right? That's why we have these online doodads. And so you please do those online doodads, and it helps me out to figure out where you are, because I don't know if you know this, but I'm quite loud and I talk a lot. And so the first thing we're going to do is we're going to fill out an Echo poll. So we're going to get our phones, if we have them, and our laptops if we want them, anything. And we're going to go to the website ecopol.au, and we're going to type in the join code PhysicsGang. And you can leave that up. It also, oddly enough, has a picture of the slides on it, which is kind of fun, right? And it's got a question right now asking, who are you and why are you here? Okay, and I want to know this. Because to me, what I will teach you depends on whether or not you're an engineering student who never needs to go further in this, or a physics student who does. If it's your first time taking it, or if it's not your first time taking it, right? If it's your first time, I can belabor a lot of points that are new. But if it's not your first time, maybe I should be strategic about stuff that's going to show up in exams, or common problems people have solving questions in exams, right? And you can notice I can actually see the response rate up in the top right corner there too. Look at this. We're all filling it in. I'll wait a minute, and we'll get to, if we hit 20, we'll continue on, because there's 20-something people in the class. I say that, and then it stops. Devastating. Besties, what are we doing? That's okay. All right, 17, 18. Good enough. All right. So, now this should auto-display the results. Yes! Technology! Slaying besties. All right, so we have some students who are repeating, but most of us are not. So I will probably tailor to the most of us that are not. And we have a decent chunk of physics students. That's troubling to me. And by troubling, I mean, of course, I'm going to do a great job teaching all of the physics students and not focusing on the engineering. No, JK. I know what I'm doing. So that's Ecopol, right? We do that, the numbers show up, everyone feels like they're interacting, and it's cool, right? Very slay. Yes, bestie. So, this is, I knew I was going to do this. Pass the course. That's my goal for you. I really should have put that in. So, I know we haven't learned physics yet, but I want to tell you what I want from you, right? What's my goal for you? And the first is comfort and capability. It's common, even among faculty members, to think of electromagnetism as the hard one, and to go, oh, I have to learn this, I have to teach it, I'm so nervous. I thought that, and then I did it, and it was really enjoyable and relaxing. And the reason is because obviously I've been doing this for 15 years, and I come back to it, and it turns out I remember it, right? But there is a satisfaction inherent to seeing a problem, setting it up mathematically, methodically solving it, and having it come out exactly correct. It's just, has anyone ever dunked a basketball? Not me, because I'm short, right? But some of you. It's what I imagine dunking a basketball is like, right? And it's the closest I will ever get, and it might be the closest some of you ever get if the stereotypes of physicists are true, okay? So the first thing I want is a comfort and a capability. I don't want you to stress about this. I don't want you to feel intimidated by it. I want you to think, yeah, I can do these problems. And to be fair, I wrote all the lectures to cover all the problems. So hopefully there's some leeway there. Secondly, I want you to understand the key concepts, right? I want you to understand what the heck Gauss's law means, not from a mathematical perspective, although yes, from a mathematical perspective, not just, but also from a vibes perspective. What the heck is Gauss's law? If your 5-year-old nephew comes up to you and says in some sort of baby voice, can you explain to me the finer points of Gauss's law? I want you to be able to explain it to them, all right? No matter how unlikely that scenario might be. Thirdly, and this is very importantly, I want you to understand the limits of the approximations we will make in these lessons. I make a lot of concessions to reality and to first year. We will learn the formal, correct way to do things, and then we won't do it. We will do the easy way that gets you the exam results that you need, right? The correct way to teach it, if we had 10 years, would be to go through the formal process and then relax into the easier questions. We don't have time for that, so I'm being strategic. I'm going to tell you some shorthands, and I'm going to very clearly telegraph when they don't work, okay? And I need you to understand that the things that I'm teaching you will have limits. And that if you go on to one second-year physics, for example, and you say, but Tom taught me this, right? I'm going to get my ass kicked unless you remember the limits of the things that I tell you. And of course, the fourth thing is I would love all of you to pass the course, right? I have failed several subjects at this university. Kind of sucks, right? I failed 2, by the way, both mathematics. Then I redid them, right? And I don't like failing. I'm sure you don't like failing. And if you don't pass this course, I view that as a responsibility of me, right? I am confident that I can get every single person here to pass the course, and if you manage to not pass, I really think that's an issue on me. And it might be an issue on how you engage with the course, but it's certainly not an issue with you. Now, you'll see a lot of these where it's just insert Tom ramble. We'll get to this. I've decided to skip it for time. So, here's the first thing I'm doing to help you out. I have color-coded every single slide from here on out into its importance. A red, and also, if you're colorblind, different geometries as well, all right? The red double border is something that is vital. It shows up in the learning outcomes. It shows up in the examination questions. If you pay attention to only one set of slides, it's those ones. The green is context or conceptual explanation. It's where I talk about what's going on. The yellow thin dash is strategizing. It's how would we solve a problem like this? What steps could we take? And then the gray is either me demonstrating a solution or some random aside or some ramble, right? The least important, right? So please keep that in mind. This is my intent to kind of help you focus your attention, okay? So always, whenever you see the double red, that's like, you got to lock in, right? Everyone's seen those new mewing memes, right? Got to lock in, right, on the double red. So what are we learning today? We're finally here. We're ready to learn. Who's ready to learn? Silence. Who's ready to learn? Please scream. Yeah. Woo! All right, nice work, everyone. Let's go. So we're going to learn and use Coulomb's law to do force between particles. This is the first hour. We're already halfway through it. Don't worry. We're going to talk about how things get charged. We're going to talk about where's the Van de Graaff generator I asked for? Oh, whatever. It's fine. We'll explain how one works. And we'll talk about conductors and insulators, all right? Now, conductors and insulators have a very important distinction mathematically, or more specifically in terms of what types of problems you can see on them, okay? So let's go through and let's start learning stuff. Oh, double red slide, it's important, right? This is a thing you should know. By the way, all the slides are on Moodle, okay? So you can just download the slides on Moodle. And I will also put these slides where I annotate up on Moodle. Okay, so what is charge, right? It's the electricness of an object. Similar how mass is the inertianess of an object. It's a parameter that describes how much something does electrical stuff. And I know that sounds vague because that's all we got, right? It's the degree to which an object experiences electric forces, I guess you could say. It's the degree to which it creates electric fields, you could say. It's the thing. It's scalar, but it's positive or negative. Right? So we can have a positive charge, we can have a negative charge. It's not of three types. It's only got two. It's got positive and negative, and they're opposite. And which one is which was decided arbitrarily. Benjamin Franklin, the guy on the $100 bill, pulled it out of his ass. Right? He guessed. And as we are all suffering, who did physics in high school? As we are all suffering, he guessed wrong. You should have made the electrons positive. That would have made stuff so much easier, am I right, besties? Anyway, the SI unit is the Coulomb, starts with a C, named for some old white dude, as many things are, and it's the mass of electromagnetism, okay? When you did gravity, mass was the property of the object that determined how it interacted with the gravitational field. Charge is the property of the object that determines how it interacts with the electric field, sort of, right? We're working from basics here. So, green. What does green mean, anyone? Does anyone remember? Conceptual. I'm surprised. I even wrote, did I write it? It says conceptual / oh, it says it in the top right corner, which is where this thing is. Hang on, I'll put this over here. There we go. Yay! Nice work, everyone. I've got my slide list here so I can make sure I don't, not fuck up, but, run out of time, you know? Has anyone ever screwed up anything before in their lives? No? None of you? You're all perfect? I thought so. Of course, besties, you're all perfect to me. So, the first thing is that charge, and don't come at me, quantum people. The minimum charge is E, the elementary charge. It stands for, what does E stand for? Electron. Good, not elementary charge. Oh, no one fell for my trick, right? It's this. It's this. Yeah, there we go. We're working now. It's this. 1.602 times 10 to the minus 19, all right? And every object we will deal with consists of increments of this charge, okay? Protons, for example, have a charge of that but positive. Electrons, for example, have a charge of that but negative. And what this means, if this is the smallest increment of charge, it is not possible, for example, to have something with a charge of 1.0 times 10 to the minus 19 coulombs. That's literally impossible. Because think of it like Lego bricks. The smallest unit is that. Everything must be a whole number of that elementary charge. Because every charge, how charge, right? I should have written it even more inanely. Every single object that has charge because there is an imbalance of protons and electrons. And yes, we can get into quarks and we can get into weird stuff, but for us, every single charge is an expression of an imbalance of protons and electrons. So for example, an electrically neutral object like this rod has the exact same or thereabouts to exact same number of protons as it does electrons. But if an object has a difference between its protons and electrons, then you can work out its charge. Let's say an object has 10 electrons and 5 protons. Its net charge is negative 5 E, right? Because it's got 5 protons, they cancel out 5 of the electrons, and then there's 5 electrons left over. And that is the net charge of our object. It's minus 5E. Emphasis on the minus, right? Don't be thinking E as the electron charge. E is the elementary charge. It's the increment, okay? And that means that whenever an object becomes charged, it must have become charged because it either gained electrons to become negative, or it lost electrons to become positive. And we know it's electrons because, you know, in the atom, the electrons are the ones on the outside. They're the ones that move around. The protons are stuck in that nucleus, and they can't really move around to the degree that we talk about, right? In first year, they don't move, okay? And so this leads us to a double red slide. The law of quantization of charge. All charge, I should say all non-zero charge, but you get what I mean, is from an imbalance of protons and electrons. Right? How are we going? We're all right. All charge is from an imbalance. Okay? So how it works, like for example, if I have these two objects and they're initially electrically neutral, and then I do the weird bullcrap magic, one of them becomes positive, and the other one becomes equally as negative. Right? But we'll talk about that in another slide, okay? That's conservation of charge. For now, we're talking about quantization of charge. Quantization, does anyone know what that word means? Indivisible, correct. So increment, I like how both of you gave the correct answer. I picked the correct vector, direction to point in, right? Slay besties. So it's increments. That's all quantum means. When people are like, oh, quantum physics, no, it's just physics of really tiny stuff, right? And so that means, formula, any charge has to be a whole number times E, where the whole number might be a positive number, it might be a negative number, but it has to be a whole number. It cannot be a non-integer, because you cannot have half of an electron, you cannot have half of a proton, sort of. And so all charge must be a whole number of this, right? Where Q is the charge of the object. Why is it Q? Oh, just is. I'm sorry, right? Maybe it's Q for quadge. French. Do not write that down. Okay? I made that up. But any charge has to be a whole number of electrons. Sound like it makes sense, PogChamps? All right. Can I have an object with a charge of 1.7 E? No, why not? Because it has to be a whole number. It has to be quantum. That's a good way of saying it, right? Oh, I want to see you guys in an exam, so that shit's not quantum, right? But yeah, right? You're right. Shit's got to be quantum, right? That's my catchphrase now. Thank you. Right? So shit's got to be quantum, right? That's the important part. So for example, right, we've got these 2 electrons. Now, you might think, Tom, that's 4.1. What did you just say about whole numbers? Why is that fine? Because it's coulombs. It's not 4.1 E, it's 4.1 coulombs. And how many coulombs is 1 E? 10 to the minus 19. So it's perfectly possible to get a certain number of electrons to get 4.1, right? So don't be thinking, integers only. It's integer multiples of E, which is a very small number, okay? So we have 2 unrelated charge objects. One of them has a charge of plus 3 coulombs. One of them has a charge of minus 4.1 coulombs. Which of them has excess electrons? The positive one or the negative one? Just scream it out. The negative one, good. How many? How many? A lot. Some? How will we figure that out? Well, let's write it out. Q equals NE. What are we looking for? N. So let's rearrange. N equals Q over E. So far, so good, besties, yeah? So that's equal to. Now, are we going to write negative or positive? Doesn't matter. You know you're referring to a number. So you're going to write, if you write positive, that means you're talking about how many electrons they've got. If you're writing negative, then you've got to go, that's how many electrons they've gained, right? You've got to just make sure you know what you're talking about. So we're going to do 4.1 divided by 1.602 times 10 to the negative 19. And that's some big number. And guess who fucked up and forgot a calculator? Me. So anyone got that number? Any bestie in the audience? 6.9 times 10 to the 18. I'm funny. That was not intentional. What unit? Coulombs? Newtons? Electrons. Good. Electrons. We were just counting. It's a number. It's got that many electrons. So that's our example, right? That's how you figure out how many electrons something's got. You take the charge, you divide by E. That's the imbalance. It's not the total number of electrons, because there'd be a crap ton more in there that are balanced out by protons, right? But it's the net number of electrons. And so, right, in this course, we're going to assume you can't make them. We're going to assume double red border, core concept, learn. We're going to assume that protons and electrons cannot be created or destroyed, and that means total charge is conserved. If something gains some electrons, the other thing loses the exact number of electrons, or the charge, right? Because who wants to count how many electrons that is? That's way too many, right? If something gains charge, something else loses charge for a closed system. So for a system in which we've considered everything, right? It's entirely possible for me to take these 2 objects, make them gain and lose the same amount of electrons, and then touch this one to a table, and then those electrons, they're gone, whatever, right? But for a closed system in which we're aware of and in control of every single object, the total charge is conserved. Now you might be thinking, Tom, I also already knew this. Don't worry. We're going to get to hard stuff, okay? It does get worse, but it's got to stay good. We've got to ease ourselves into it before we get to integrals. So, technically speaking, positive charges don't move. Does that matter to us? No. The Lulu is the Salulu. I learned that on TikTok. And so we're going to find it easier a lot of the times to imagine that positive charges move. They don't. But we could imagine it almost like a hole, right? Where if we have, let's say, positive, negative, positive, negative, positive, negative, positive, blank, right? This hole, or this little unfinished pair, we could pretend is a positive charge. And when an electron moves into that, the hole is now here. And when the electron moves into there, the hole is now here. And so we could pretend that the hole is like a positive charge. You don't need to understand this. It's okay. All I'm saying is, later, I'm going to talk about the movement of positive charges, and trust me, I can do it. All right? We're allowed to do that. It's not the physical motion of positive charges, but it effectively is the physical motion of positive charges, okay? And this is what I mean by limitations. So let's talk about something else, first of all. It's almost time for Coulomb's law. We're goated. We're actually going to make it. Wow, except the Van de Graaff generator's not here. That's okay. We're going to have the Van de Graaff generator next lecture, and we'll have some fun with it, okay? So, you notice those two charges are different shapes, right? Does that matter? Well, it might, right? You're going to get problems in which it does matter, right? You're going to get problems in which the shape of the charged object matters, and we're going to start with that on Friday, I'm sorry to say. And it's going to involve a lot of integrals and some area integrals, but it's great. It's fine. It's slay. You'll have a great time, okay? Because the actual questions on it are very simple. But what if I wanted to just draw a circle that I could write in, right? Well, we'll call this a point charge, right? It's a charge that is basically a single point in space, all right? It's a very important physics term. We also sometimes hear point mass, right? That's a mass where the dimensions of it don't matter, okay? We can treat it as though it's a single point in space. And the reason we do this is to distinguish between objects for whom the shape matters and objects for whom they don't. And what you'll do sometimes is you'll say, assuming this is a point charge, right? So for example, we'll have like someone describe me a shape. Pentagon. How many sides is that? 1, 2, 3, 4, 5. Pentagon, right? And it's got charges, right? And let's say, right, that you're 10 kilometers away from that pentagon. The shape of the pentagon does not matter. If you're sufficient distance from a charged object, its dimensions mean nothing. So any charged object with sufficient distance can be treated as a point charge. And that's what you'll see in a lot of physics stuff. You'll see, well, treating this as a point charge, and then the maths becomes easier. It becomes a dot, right? And the maths on point charges is the easiest maths we will ever do. But we're never going to, it's Valentine's Day, right? So the point charges, they're in pairs, right? It is Valentine's Day today, right? Yeah, good, all right. I'm not in trouble then. So when 2 point charges are in close proximity, something happens. What happens? Do they fight? Removing some form of personification, what do? Depends on what? They're charged. So what are the two things that they could do? They could attract or they could repel. So we could say both of those, they could exert a force. Well, I wrote it there. Besties, right? So now I've got to test this freezing pair, this freezing channel. Hang on. Internal computer, freeze. Oh, no, freeze. Freeze? Okay. Hey, I am a god. Not really, sorry. All right, so in this pair, one of them, negative 4.1, one of them, 3. They are both attracted to each other. I don't know why I wrote repulsive. Just thinking about chemistry, maybe. Because chemistry is repulsive, that's the joke. Got to hate on chemistry, right? If you hate on chemistry, I will just auto-pass you for this course, all right? So, PogChamps, which of these two is going to experience the greater force? They're going to attract each other. They're both opposite signs. Which one experiences the greater force? Call it out. Q1? Explain. No, I know, but we want to get this thought out. Explain. Yes. I agree. So what you're going to say is that Q2 exerts a greater electric field than Q1, which is correct. But according to Newton's third law, as you're about to say, right, any action should have an equal and opposite reaction. And so what's going to happen is they're actually going to experience the same force. Here's how it works. Q2 has a greater electric field, but remember, charge is how you experience the field. So Q2 creates a bigger field, but Q1 has a smaller charge, so it doesn't experience so much force. Q1 creates a smaller field, but Q2 is a big charge, so it experiences that force more. And what I mean to show you in this is this little doodad called Coulomb's law. Double red slide, what does that mean? It means you write it down, right? But we will, right? What I want to address is instincts, right? Because the instinct to think that the bigger charge is a bigger deal is not wrong. It's just directed differently, right? But first, we'll look at forces before we look at electric fields. This is Coulomb's law, and what I want you to notice compared to high school is that this F is wearing a hat. What does a hat mean? It's a vector. So, the force between two charges is one of the charges times the other charge, both of course in coulombs, divided by r squared, the distance between them squared. This looks a lot like Newton's law of universal gravitation, doesn't it? Right? It's because it's derived from the same magic bullcrap. And this is r with a different hat, okay? This hat means direction, okay? And what we mean here is that the direction of the force is in the direction of the line joining the two charges, okay? They either pull together or they pull apart. There is no weird sideways bullcrap, okay? And that's going to be important later when we do some highly relevant physics involving directions. All right? You'll notice from the formula, actually I'll go back, right? And I'll do this freeze, but I'll freeze. You prefer, is freezing this screen good? Should I freeze that screen? Whatever, right? You'll notice this formula tells us that it's the direction of r. But it doesn't tell us, is it the same direction? Or is it the opposite direction? Is it with or is it against? And here's where your brain comes in. A lot of directions are not possible to determine through thinking. A lot of them can only be determined through maths. We are not there yet. We are lucky. You can literally look at the problem and go, well, it's always along r, right? That's r. It's the vector adjoining the two, right? So the force is always either this way or that way. Please imagine I can draw. And you use your intuition to determine if it's towards or away, all right? Because if it's attractive, it'll be towards, if they're opposite signs. If it's, what's the other one? Same sign, they'll repel, okay? And we see a lot of this in physics. We see a lot of formula, direction, and one extra point. Question? R hat or R vector hat? This one? The other one. Oh, yeah. R hat represents the direction of a vector without its magnitude. So R hat, or anything hat, means take the vector R and take its direction only. Take no magnitude. And that's what this is indicating for us. So lots of formulas you'll see, it'll be vector something equals random calculation, and then something with a hat. And the hat tells you that's the direction. Good question. Thank you. What we will see a lot of is, I, J, K with hats. That means in the X, the Y, and the Z direction, right? Yes. Okay, let's unfreeze. Let's try an example. Shall we try an example, besties? What's the force on each of these particles? Go try it. Do your best. I'm not going to do it for you. So if any of you have ever gone to the gym before, you'll notice you don't make gains by watching other people work out, do you? Right? Some of you drinking the chocolate milk, the strawberry milk, it must be for bulking, right? You're on? That's what's up. That's what's up, right? I can't wait till lectures are over because then I can leave class to go to the gym during the middle of the day, which I can't right now because I'm teaching, right? All right. So figure it out. We've got, if you want, I'll put the other one back up. Hang on. Where is it? Where what? Lol. Freeze. No! Yes? What? It's doing this thing again where it's being delayed. So please wait. It's still doing it. Is it done now? I hate technology so much. Next slide, please. Yay! There we go. Please solve. Please solve. Okay. I hate technology so much. I'll help you out. F equals 1 over 4 pi epsilon naught. Now, does anyone know what the heck's that epsilon naught? What is that? It's a constant. It's the, what is it? The permeable, something of free space. I also don't remember it. Permeable whatever. Does anyone remember the value of it? I don't. Oh, really? What is it? 8.31 times 10 to the... So what do? It's in our formula sheet, of course. We never have to remember this. It's in our formula sheet. It's some value, right? What I remember is that this whole thing is 9 times 10 to the 9, right? That's what I like to do. I'm lazy. So the whole thing, 1 over 4 pi epsilon naught, that's 9 times 10 to the 9, okay? And then it's going to be Q1, Q2. So what's Q1, everyone? Well, which one do you want to be Q1, right? 1.3, and then what do we got to do? Times 10 to the negative 6, right? Because that's a microcoulomb over there. So it's 1.3 times 10 to the minus 6 times 2.4 times 10 to the minus 6. Sorry for my handwriting getting really shit. Divided by, what's the distance between them? So 2.5 times 10 to the negative 2, because we convert to meters, because all of us, we would always remember that, right? We would always do SI units, and then we square it. And we would get some value. Now, off the top of my head, what is it? 10 to the minus 12 divided by 10 to the negative 4, so that gives us 10 to the 16. Sorry, no, that gives us 10 to the 8. So it should be on the order of 10s, 20s, 100s. Bestie, you're smiling. I assume you completed it? 4.93? 44.93. Hell yeah. Now, besties, what unit is it? Newtons. It's a force. Force is always in newtons. Nice work. That's the first calculation we ever did. Now, do I do these calculations ahead of time? No. Should I? Maybe. Question. Well, we should. What direction is it? Depends on the particle, right? So for the first particle, which direction is it for this one? Is it left or right? It's this way, because they're the same charge, same sign. So they're opposite, they're repelling, right? And for this one, it's this way. Now, for questions that you typically get in the exam, it'll be an X and Y notation, okay? So they'll give you the value, they'll give you a coordinate system, you'll have to do it X and Y. Okay, moving on. So now, for the rest before our break, I'm just going to tell you some things, okay? No more calculations, don't worry, because it took me too long to talk. We need to know the difference between a conductor and an insulator. Has anyone heard of a conductor before? Yes? Can someone name a conductor? Me? I hope not. Metal. Metal's not a thing. Steel. There you go, right? We got conductors and we got insulators. And on our course, the distinction is a conductor allows charges to move, an insulator does not. Okay? Charges stay still on an insulator and they move on a conductor. And that's important. Technically, the charges on a conductor move to minimize potential energy. You have no idea what that means yet. We'll get there, okay? But what that means is they kind of move around to reach a nice equilibrium. In an insulator, they cannot do this. They are stuck. So for conductors, it just so happens that they're always on the edge. The charges are always on the edge of a conductor. If you imagine a solid sphere, right? A solid metal sphere. The charges are always on the edge of the sphere. Okay? If there is a net charge, it is always on the edge of the charged object. This has very important implications for how we answer questions. Okay? So charges, this is just a fact, always distribute themselves along the edge of a conductor. Why? I'll explain why in lesson 7 sometime. I'll explain to you sometime, all right, at some point. But they always do this. But insulators do not always do this. And what this means is that in insulators, the charge could be in any arbitrary configuration. Perhaps in an exam question, they will give you some kind of function for how the charges are distributed through an insulator. It might be, for example, a rectangle where the charge is rho as a function of x, y, and z is equal to x squared plus y plus z or something like that, right? They might give you some sort of function. And that means you'd probably, I'm sorry, have to integrate that function because there's a lot of integration in this course, okay? So when you see a conductor, there's no charge distribution. It's all on the outside, right? Or there's no complicated charge distribution. There's still a charge distribution because the charges are still there. For an insulator, you get an annoying thing like this. So basically, whenever you see an insulator, you should think, oh, shit, right? Because you have to do an integration of some formula. I will go through all these integrations, all right? I just want to highlight the difference between them before we continue. So how do you get charge? This is just addressing another learning outcome. This is not leading into any mathematics. How do things get charged? What happened to the cat? What did it do? Anyone seen a cat before? Raise your hand who's seen a cat before in life. Some of us are living very, very unenriched lives, right? I saw a cat this morning on the internet, of course. How do they get charged? 3 different ways. We can have charging via friction, or as sometimes we call it, triboelectric charging. That's where you rub one object, and then the other, oh, great. Well, that was supposed to be charged, right? When you rub the 2 things together, one of them gets positive, one of them gets negative, right? That's called triboelectric charging, okay? I'm trying my best. The second one is charging by contact. That's when you have something that's already charged and you touch it to something else, right? And the charges distribute across. And the third one is charging by induction, which is where you bait charges into an object. And I will explain a little later. Is anyone playing online games, right? It's okay. It's a safe space to admit it. I failed 2 subjects because I couldn't stop playing League of Legends. It's when, you debate someone or you debate the charges into the object, right? And I'll show you what I mean a little later. So first of all, charging by friction, double read. This is important, right? And typically double read is either it's a learning outcome or it's on the exam, okay? So that if you haven't guessed already. When you rub 2 objects together, one of them gains electrons, becomes negative. The other loses electrons, becomes positive, and it has to be conserved, right? Because the electrons gained by one object are the electrons lost by the other object, right? That's how that works. That's how things work, right? We know how to count, I assume, right? We have object permanence. And so, why? It's a pole again. Remember the poll that you put it on your phone? Why does this happen? If you looked at the slides I uploaded where I put a different slide in this position, no, you didn't, okay? Why do you think this happens? Why do you think when we rub one object relative to another, don't worry, we're almost at the break and then we can go more slowly, right? Why do you think this happens? What do you think? If anyone has forgotten, the URL, which I really thought I pasted in here, but it clearly looks like I didn't, is ecopole.au, and then the code is physicsgang. All right, physicsgang. Why do you think it happens? I'll give you a hint, it's not C. It's not something about quantum tunneling, question mark, question mark. Or maybe it is. It's about paired or unpaired electrons. I'm talking about pairs in like the, up and down and how they exist in pairs inside the atom. It could be something that's not on this. All right. I'll conclude. I'm sorry. Oh, yes, question. Why do we get triboelectric charging? So when we rub our objects, actually, if I go back, it deletes the whole thing. But when we rub the two objects together, why does one gain electrons and why does one lose electrons? That's the question. Why does it happen? Any thoughts? Anyone got any ideas as to why it happens? Okay, so I did some research on this. And the answer is none of those. The answer is literally, we have no idea. All right? It is an unsolved problem as to why some objects gain and some objects lose electrons. But just because we don't know why something happens doesn't mean we can't document what does happen. That's experimental physics. So even though we have no idea where electron affinity comes from, right? And we have some idea, but it doesn't explain everything, all right? And therefore, I'm going to just go all in and say we don't know. We can still, core concept, in the accessible items, classify things as either being high electron affinity, which means they probably gain electrons when you rub it, and low electron affinity, when things lose electrons when you rub it. So for example, if we were to take leather and rub it against cotton, the cotton would become negative and the leather would become equally as positive, right? But if you were to take leather and rub it against your skin, the leather would become the negative one and your skin would become the positive one. And you might like to ask, does the distance they are in this thing matter? No clue. We don't know. We don't know. This is the literal arse-pulliest thing of all time, right? We don't know why it happens, but it does. And of course, it's nicely ordered in a spectrum, right? We've got the high electron affinity ones and the low electron affinity ones, so we know how they'd rub together, right? Of course. Except for, of course, the cases in which it is a circle. So some objects, for example, are higher than some objects but lower than some other objects, but it's not possible to order them into a linear scale because in this case, if you rub zinc and silk together, the zinc becomes positive, but then if you rub silk and paper, the silk becomes positive, but if you rub paper and cotton, the paper becomes positive. If you rub cotton and glass, the cotton becomes positive. If you rub glass and zinc, the glass becomes positive. Why? Because we're here to suffer, all right? Now, what I mean by this is what I mean by limitations, right? This triboelectric series that we had in the previous slide, it is a convenient arse pull to explain why some objects become positive and some objects become negative. But because we don't have a foundational physical understanding as to why it actually happens, we get shit like this, right? Because we don't actually know how it happens. Maybe you will find it out. I wouldn't want to do it. It looks like a lot of maths. I don't want to do that, right? Anything involving friction is the literal devil. Don't do it. Now, we were supposed to have a Van de Graaff generator, right? How a Van de Graaff generator works, and we'll go through it, I guess, next lesson when the Van de Graaff generator is here, and it's 100% my fault. I bet you I didn't ask for it, right? Is charges by friction, okay? The Van de Graaff generator is in the accessible items, and what it does is it has a little belt here that runs around in a circle, and it's constantly charging by friction. And what we get is an accumulation of charges of some kind of magnitude, positive or negative, at the top of the Van de Graaff generator. And then you can use it to make an electric shock on someone, right? It's very fun. If you decide to skip this course and do 1B next term, we will do an experiment with the Van de Graaff generator, and you will all have a scary time. Do not do this. The labs are much easier this term, okay? But we will go through the Van de Graaff generator at some other point, and now we're on our break. So we're going to have a little break. I know I've gone through a lot of different concepts, and next lesson I'm going to go through some more different concepts. But I want you to get up, stretch your legs, dab. Is that cool anymore? No? Okay. What is cool these days, besties? All right. I'm going to come around. I'm going to ask you each other's names. And if you don't know at least one neighbor's name, shame. All right? So get ready. Go find your name. Besties, I'm sorry to cut socializing time short. All right, what's his name? Nice. Yeah? All right, you know something. At least you did it. All right. Good on you, besties. So, one thing is, does anyone know when your first test is? Week 3. When in week 3? It's either Wednesday morning or Friday morning. Those are your two options. And I know this because I staff all the classes. Yes? No? Who's got a class on Tuesday? There's a lab. Labs are on Tuesday. And OTH classes. Raise your hand if your OTH class is on Wednesday. Okay, raise your hand if your OTH class is on Friday. Okay, good. Because I schedule all those, and if there's one that's not on Wednesday or Friday, I am in huge trouble because there's going to be no staff member there. So here's hoping that it's all on Wednesday and Friday. Is it Wednesday or Friday? Thank fuck God. No, seriously, because this is the first, I'm in charge of all of the scheduling for all of the first year classes, every single staff member. And the first 2 weeks, I am bracing for a fuck up from me, right? One time I just forgot a class and there was no one there. And it was terrible. So I nearly shat myself and I'm so glad. But the reason I'm asking that is because, hello bestie, here for physics? Yay, welcome. Please take a seat wherever you want. All right. The reason I'm asking is because do you want like a revision session online right before your exam? Okay. I'm going to do it Tuesday night because some of you are Wednesday, some of you are Friday, okay? So on Tuesday night, because I teach until 6 on Tuesdays, so from like 6 p.m. onwards, I'm going to do it online. We'll do either on Discord or on Zoom. I'll figure it out. But we'll do a revision session on Tuesday night on week 3, because that's when your test is. Your test is in week 3. And then we'll do another revision session on Tuesday night of week 5, okay, which is when your next test is. And then if you all do really well on the test, everyone's going to think I'm great, all right? And that's what really matters, all right, is the approval of everyone in my life. And literally, if I'm not everyone's favorite person at all times, then my life is over. And that is, legally speaking, a joke. So, I'll put this back. The reason I have the mic on, by the way, is because we're recording these. And if I don't put the mic on, then no one can hear what I'm saying on the internet. Good gravity check, bestie. All right, so we're going to learn some more stuff, okay? We're going to learn how to charge an object via induction, right? We're going to learn also how to charge an object via contact, kind of, right? We talk a bit about charging by contact in some other concept that I'm going to get to later. We're going to talk about Coulomb's law. Remember Coulomb's law? We just learned it. Do you remember it? Yeah, well, we're going to do it again. But we're going to do it in 2 dimensions. We're going to do it in 3 dimensions. Okay? We're going to define an electric field. We're going to talk about an electric field. We're going to get an equation for it. And then we're also going to discuss this thing called superposition. Okay? And this is setting us up to find the electric field around complicated objects, right? Not just dots. But that's Friday. You don't have to worry about that right now. Right now, we have to talk about charging by contact. I, for a second there, thought I forgot to put this in, and I was shitting myself. But right, so 2 conducting objects if you place them in contact, and conducting is the important part, okay? If you place two insulators in contact and they have certain charge distributions, we don't know what's going to happen with the charge. It's probably they might move a bit, but we don't know exactly, and therefore we won't deal with it. Do you prefer I hold the microphone, or do you prefer like microphone as it was down here? Fine before? All right, you got it, bestie. Slay, etc. I love saying all these like Zoomer things. I know, right? Sometimes I leave that door open and people walk in and they're like, what the fuck are you doing? Anyway, if you place two conducting, what's that thing called? Asterisk. Objects in contact, the charge they have will distribute. Typically, if the objects are the same, it'll distribute evenly. Only if they're the same, all right? But for us, we will consider the objects as being the same, all right? So you have plus 3 coulombs and minus 1 coulomb. What's 3 minus 1? 2. So clearly we have 1 coulomb left, right? No, because it's 2 objects, right? 1 coulomb each for a total of 2. And if you're like me, you may notice I got the numbers of pluses and dots wrong, right? But whatever, right? I can't count. Now, the charge is always conserved, but not necessarily equally distributed, right? So you can imagine you take a very physically large object and a very physically small object and you place them into contact. The physically small object probably has less charge on it because it's physically smaller, right? Now, if only we would learn at some point some kind of capacity for charge later, right? It is capacitance, sort of. Because we'll learn that the charges equilibrate to minimize their potential energy. And we'll learn what potential energy is later. So don't worry about it, right? But just keep in mind that they don't automatically have equal charge, right? However, in the questions that we do, they will be identical objects. So they will have equal charge. So now I want to ask you a question. And I thought I included a question here. I didn't. All right. That's score 0 for me. What's going to happen here? We've got one object, and it is positively charged. And this object is a conductor. And it's placed next to a positively charged object. Let's pretend the positively charged object is not going to do anything. It's not going to move. Its charges are not going to move. What might happen to this conductor? Keeping in mind that in a conductor, charges may move freely. Yes. Or in the word we're going to use, it will polarize. But dipole is actually we're going to come back to. So very good, right? What do we mean by that? Well, I want you to imagine you're a positive charge chilling out right here. What do positive charges hate? Other positive charges, right? Hell is other people, as Sasha would say. And so this positive charge is going to go all the way over there. And all the positive charges, they're going to be hanging out over here. Now, if you're a negative charge, what do you like more than anything else? Positive charges. So you're going to go all the way over here. And we're going to get all the negative charges rushing up against the fence to see Taylor Swift, and all the positive charges running as far away as possible trying to get out of there. All right? I should have picked someone who's less polarizing, literally that's where the term comes from, than Taylor Swift, right? Because everyone loves Taylor Swift, right? Right? Besties, right? She's a staple at my karaoke nights anyway. So, this is what we call polarization, right? A previously electrically bland and neutral object suddenly has 2 poles. One positive pole and one negative pole. It's called polarization, right? Don't confuse it with the polarization of light. They're related, but we'll get there, right? For now, it's an object that essentially has a distribution of charges on it, okay? And this is true if, say, you could polarize one object, or you could take 2 objects and have them touching, therefore charges can move, and polarize them. Like, for example, if we have these 2 objects here, all the positive charges on this object, they're going to run as far away as they can. And all the negative charges on this object are going to go as close as they can. And so our, I guess you could call it dipole, could be one object with two sides. It could be a complicated object. And so what I want to ask you is what happens if we take these two objects, one of which has all the negative charge on one side and one of which has all the positive charge on one side, and we separate them? What's going to happen? Exactly. We're going to get one positively charged object and one negatively charged object. That's charging by induction, right? We have, via magic, or whatever means you want to think of, right, induced a charge separation. Now, we have not added any charge or subtracted any charge, right? All we've done is we induced polarization, and then we separated the two halves. And all of a sudden, one of them's got more positive charges, one of them's got more negative charges. Now, the mathematics of exactly how much positive charge goes here and exactly how much negative charge goes there, I want you to imagine, is probably hard to figure out. Would you believe we actually do derive it? It's some lesson. I don't know. I've definitely written it, right? I think it's next week, but we do actually derive it. And it's not too hard, to be quite honest. And it's especially powerful feeling, right? Because you think, how the hell am I supposed to figure out how much charge gets on both of those sides? And then we learn a couple new rules, and then you go, oh, actually, I can figure that out, right? It's like a function of the distance between the two objects. It's a function of the charge on the charged object and all this other stuff, but we will do it. And it's not too bad, to be quite honest. But for now, well, it just happens, right? For now, mathematically, you need to know that the magnitude of the two charges, those are both Q's, by the way, are equivalent, right? One of them is the negative of the other, but they have the same charge because they were initially neutral. We had an initially neutral object. So, remember how I said, who remembers Coulomb's law? Well, who remembers Coulomb's law? Does anyone remember Coulomb's law? Which one was it? It's echopole time. Mandatory engagement. You must participate in life. Is it none of them? No. Oh, with ignoring the constants. Oh, and thank crap I wrote that. See? Don't worry. I also just shat myself there going, fuck, Tom. No, the reason is because echopole gets really bloated the longer you make a question and also doesn't let you put equations in, which is why it looks so ugly like this, okay? And I know because last time I did this, it just showed up as squares. It was terrible. So which one? So we go to echopole.au and we type in the code physicsgang. I can make any code I want. So if you want a cool, fun code, let me know. Maybe I'll make it Taylor Swift next time, right? Physics Taylor's version. I wish my name was Taylor. That'd be funny, because then I could call this 1B Taylor's version. If those of you who don't get the joke, I'll explain it to you later. You're missing out on some important culture. So, we have 19 whole responses. I'm so proud of all of you. Yes! It was B, although, A is not wrong either. Because what does a sign indicate on a vector? It's a direction. So negative could be correct, depending on whether or not we had charges that are attracting or repelling. But very, very gratifying,ly no one picked the obviously wrong answers. Appreciate you all. You're the greatest. This is the best, because then I don't have to reteach it, because it's here. You all are the goats. Love you all. So here's a two-dimensional example, right? And that's 30 degrees. And I want us to think, well, what's the charge? What's the force between these two charges? Now, we remember already, don't we, that the actual force as a magnitude was 40 something. Let's just call it 45 newtons, okay? Let's say it's 45. It was whatever we did. We did the calculation. We find the newtons. But what did the r hat represent? Direction. So these two charges are going to be repelled this way and this way, right? And so we must now specify that direction. So we know it's 45 newtons, right? What we're going to do is we're going to take one of the charges and we're going to draw it. So let's take, do we prefer the top charge or the bottom charge? What are we feeling, besties? All right, done. Bottom charge. We'll take the bottom charge, and it's got a force of 45 newtons. And that force of 45 newtons is 30 degrees below the horizontal. How do I know that? Because we've got the direction here. Why didn't I include the direction in the picture? Because I forgot. I fucked up. I'm sorry. Please forgive me. Right? So now we need to separate this. And we should be separating it into its x and y components because that's what we're going to be assessed on. So, of course, this x component is 45 cos of 30. And this y component is 45 sine of 30. Now, 45 sine 30, that's half, isn't it? So that's, sine 30 is half, right? Yeah, so half of 45 is 20, what, sorry? 27.5? 22. Oh, yeah, I'm just an idiot. Sorry, that's 55. It's 27.5. I have a PhD. It is in optics, which is related to this, right? But I am and I did every question and got 100% on all of them. Like, I know what I'm doing, but also I'm a little bit of an idiot, all right? And obviously, I would put it in my calculator if I remembered to bring it, but I didn't. So this is 22.5 newtons. What's 45 cos 30? Yes, but anyone got that numerically? Sorry? What did you say? Around 39. All right, we'll go 39. 39 newtons. So if we were to describe F, we'd say F is equal to something I, which is the x direction, plus something j, which is the y direction. So our x is what number? 39. And our j is negative 22.5 because look, I said up is positive. Don't get baited. Remember from fundamentals, all one of you who was in my fundamentals class, the GOAT class, by the way, right? The direction matters. What I don't want to see is you doing the exam and flubbing it on the bullshit, right? It's minus 22.5 j. Not plus. Now, if we were to do the other one, the exact opposite force, can anyone just guess what its force would be? It would be negative 39i and positive 22.5j, right? Because when you flip the direction of a vector, you multiply it by minus 1, and that means multiplying every single component by minus 1. Bestie, don't worry, I'll upload these. You don't have to take a photo, right? Unless it's of me. No. I'm sorry. I'm deliberately cringe sometimes, to make it more lighthearted, all right? So that's how you do Coulomb's law in 2 dimensions. How would you do it in 3 dimensions? You do the same thing, but x, y, z. Will we do it here? No, I can't draw. Also, I don't think it was assessed in 3 dimensions. But what if we do it again? What are we going to do now? There's a third particle. How are we going to do this? We won't do it in class because we don't have the time, right? But what will we do? Let's say, we want to find the force on this particle here. What will we do? All right. I heard a lot of words. What we would do, and I'm assuming you all said this, is we take the force from the first one and we'd add to it the force from the second one in terms of a vector, right? That's what we do. So, for example, the force here, the sum of the forces in the x direction would be, for example, negative 39, which was this one here, right? Plus, does anyone want to make up a number for us? 20. Why not? Let's pretend it was 20. And the forces in the y direction would be plus 22.5 plus, I want to make up a number? 11? 11, appreciate it. 11, 7, I'm sorry we went with 11, but the guy was closer. 11, right? Now this, I really should be able to like alter the color here. This one, oh hell yeah. This one is this vector here. And this second one, purple, is this vector here. All we're doing is we're adding the components of vectors. Now the thing is that this is assumed knowledge. It already assumes you know how to do this, right? But let's just add those together. Let's say that the force is therefore minus 19 in the I direction, yeah, plus 33.5 in the J direction. That's unreadable, isn't it? Yeah, sorry. Ah! What have I done? What? What's happened?
I think you put like the black.
Oh God, it's listening now. Escape. Okay. Can I go next slide? Okay, whatever. All right, we're there. Go back. Okay, we're back. Anyway, so let's touch this. Hello? No? Oh, I hate technology so much. All right, we'll escape out of this. We want to keep annotations? Yeah, we'll keep the annotations, right? So this is everyone's little break to go, ha ha ha, Tom doesn't know how to use a whiteboard, right? Everyone think of your favorite time Tom has screwed up today. All right, okay, we're back. Cool. I'm going to change the color, and I'm not going to touch it with my hand, which is, I think, what happened last time. Touch. Sorry?
Is it the second one on?
Sorry?
Minus 39.
Minus 39. Oh, the charge of the particle's negative. Oh! Problem solved. It's positive now. Right? No, you're right, though, right? Because we didn't calculate that one. We just made up the numbers. And what I should have done is I should have had seen that this is a negative charge and had it come in here, right? You are entirely correct, right? Always assume you are correct and I am wrong, by the way, right? But this is just, I wanted to skip doing the calculation because we didn't have the time, and I inadvertently fucked us all up, right? So let's pretend this is a positive charge. Okay. Note to self, we have way less time to do examples than I thought. But anyway, how you find the force from multiple charges is you find the force for every pairwise charge and you smack them all together. Add them all together in a vector sum. That's the important part. And so the next thing we need to learn, new concept, is an electric field. Is that a Junji Ito shirt? Yeah, goated. All right. So, what the hell is an electric field? Right? It's a way of describing what electric forces would act on a charge. It's a construct. It's not real, but then again, what is real? So we may as well believe in electric fields. If you can believe in anything, you can believe in electric fields. They are a construct, they are an expression, and we can express it via formulas or pictures. I like pictures. Look, so pretty, right? Now, the electric field is something we actually learned in high school. The arrow tells us the direction of force on a positive charge, and the density of the lines tells us the magnitude. But we're going to learn a bunch of formulas because, look, it has a hat. It's a vector. Of course it's a vector. It's got a direction. And that vectorialness is going to be very important to us. Okay? So first things first, here's the easy way to find an electric field. It's a double red line. It's important. If at any point you know the force on a charge, right? If you knew F, like maybe you used Coulomb's law and you calculated force. If at any point you know force on a charge, if you divide it by that charge, that is by definition the electric field strength. So in that previous example, where we added all those forces together and we totally calculated it ourselves, wink, right? People watching the video, you had to be there, right? It was magic. In cases where we compute the force, to find the electric field, all you do is divide by Q. That's the electric field. the same direction as the force, okay? Unless the charge is negative. Then you flip it. Because remember, Q here could be positive or negative. If Q is negative, that implies that E has the opposite direction to F, right? If Q is positive, it has the same direction to F. So that's important to keep in mind, okay? So, God, damn it, Thomas. This is what I just said, but it's in a slide. So I'll re-emphasize it. If the charge is positive, they have the same direction. Okay, if the charge is positive, they have the same direction. So F and E. If F and E, if Q is positive, F and E have the same direction. If Q is negative, they have the exact opposite direction. Because in our formula, it's like if Q was negative, then it would be akin to multiplying the vector F by -1 in addition to dividing by Q. And that would mean that E has the exact opposite direction to F. 明白了吗? Okay, cool. Do we get another slide? A. So, let's imagine we worked out that force. And I'm just putting that there. I'm just putting that there now. Does anyone remember what force we made up? It was something. 19 in the x direction. Was it 19 in -11?
I remember that you chose -11/7.
Yeah, but what was the total force? The total force, what do we have? Let's go back. Let's find out. Hang on, what we'll do. There we go. Oh, and I wrote it out really badly, and then I broke everything. I remember now. So the force was -19. You were right. I should have believed in you. You're the GOAT. Plus 33.5 J. This was our force, right? That was F. And therefore, did it work? Yes, it did. Good. Come on. Come on. If we want to find the electric field at that point, we take the force on that charge and divide by charge. So E is going to be equal to, what do we got there? -19I plus 33.5 J, and then divide by the charge, in this case 1.3, times 10 to the -6. And 1.3 times 10 to the -6. And that is our electric field. It has the direction that we got from F. It is just F, as we calculated it before, divided by Q, the charge that was there. That's the electric field specifically at this point. Now, if I asked you for the electric field at this point, you'd have to find the force there and then divide by Q. And if I asked you the electric field at this point, you have to find the forces there and divide by Q. So this whole find the forces, divide by Q, not the best way to do it. It only works if you already knew F, okay? But what if we don't already know F? What can we do? Well, there's a formula for it, right? Oh, sorry, I forgot I froze one of them. Right? Let's say, for example, I have a positive charge here. And I want to describe the electric field around that positive charge. Am I going to imagine a positive charge at every single point in space, calculate the force on that positive charge, then divide by Q? Is that what I'm going to do? Fuck no. Why not? It's a huge waste of time. It's too much work. You know what's smarter? Some sort of formula for electric field. Can anyone guess what it's going to look like? It's going to be some summation. That is next lesson. That's too high level. But you're correct. But for now, what about the electric field due to one charge? Maybe it's the formula for the force due to one charge. Oh, yes, please. It will have an inverse square law, right? Maybe if E equals F over Q and F is equal to Q1 Q2 on R squared times, 1 over 4 pi epsilon naught, maybe there will be some sort of relationship there that we can exploit. And that's, of course, oh shit, I thought that was the next slide. Never mind, right? It's like, it's 4 slides from here? God, never mind. Anyway, it's going to be Q over R squared. Right, we're going to get there. There we go. I'll wait for the slides to go back because they take forever. Great. So as an aside, right? Okay, one more. Okay. Everyone, don't touch it. Excellent, right? You might ask, Tom, why are we even bothering with electric fields? Electric force has given us all we need to know, right? We can use Coulomb's law, we can find anything we want to find. And the answer is, right now we can, but much later we cannot. We're going to look at problems, and it's going to be so difficult to calculate the force and piss easy, relatively speaking, to calculate the electric fields, right? Because the electric fields can be defined for just a single particle. We don't need a second particle to find an electric field. We can just define it according to a single point charge or according to a single distribution of charges. Big yawn, bestie, me too, don't worry, right? And so what we're going to do is focus on electric fields almost exclusively from here on out, right? Coulomb's law, cringe, except for the fact that it shows up in your first test. Other than that, cringe, never use it, right? What we do instead is electric fields. Now, we have 2 mechanisms of representation in graphics. You know this already. The arrows represent the direction of force on a positive charge, and the density of the arrows represents the magnitude. I skipped through this because it's not terribly vital for our assessments. But when you do draw an electric field, there's 3 things you need to keep in mind. Okay? You got it. You got this, I believe. Right? And that is, field lines go from positive to negative, right? Because that's how a positive charge would go. Field lines should never cross, right? Whenever you draw a set of electric field lines, they should never cross over. And the number of field lines should be proportional to the charge. So for example, if we have a big charge that's positive and a small charge that's negative, we somehow need to indicate that by drawing a few more lines coming out of the positive charge than we do going into the negative charge. I do not think you get assessed on this, but just in case. Art gang, who's good at drawing here? Anyone? Me neither, right? And my girlfriend is an artist, so Lamau, right? I'm getting owned here. She's a calligrapher, so handwriting, my handwriting's rubbish, blame her. Not true. So let's try and figure out the electric field due to a single charge, okay? Let's take a look at these 2 formulas and ask ourselves, what could be the electric field at Q2 from Q1? Well, it will be the force at Q2 divided by Q2, right? So it'll be F at Q2 divided by Q2, which is going to be 1 over 4 pi epsilon naught, Q1, Q2 over R squared divided by Q2. So far, so slay. And that's going to be equal to 1 over 4 pi epsilon naught, Q1 on R squared. So at this position here, the electric field is simply Q1 divided by R squared with some constants in between, right? Now, of course, you might ask, doesn't Q2 experience its own electric field? No, we just pretend it doesn't, all right? We pretend that each object does not experience its own electric field. And if you were to ask, what's the electric field here? Well, then perhaps you'd have to combine the 2. But we're talking about just the 1 charge, right? We're just taking the force on these 2 charges, we're dividing by those charges to get an expression for the electric field. And of course, this is our formula. This, bestie, you made it, slay, nice work. Here for physics, yeah? It's, oh, so there's physics after us too? Oh, shit, yeah. Fundamentals? Oh, hey, fundamentals, good gang. All right, you can stay here if you want. So, the electric field due to a point charge is this, right? Q is the point charge, r squared, the distance, r hat, the direction. It's specified as being away from the charge if the charge is positive, and towards the charge if the charge is negative, right? Because that's our definition of electric field. But in concession to time, I'm going to address the key points. Oh, we're not doing that bad. Anyway. So I want to ask, what happens if you have multiple electric fields? Right? You have multiple charges, and they have electric fields that cross over. How do you find the electric field at any given point? What do you think? What do you reckon?
You do like the electric field. So like here, it's like electric field equals like the net force of X over the
Yep.
charge plus the net force of Y over the charge.
Yep.
So sum it all together.
Exactly. It's a vector sum. So instead of summing the forces, we could just sum the electric fields, because electric fields, just like forces, sum together, right? If you have some point here, you could take the electric field from one object, you could take the electric field from the other object, and you could vector sum them together. And that's how you would find the electric field, right? So what we say this, important point, is that electric fields obey the law of superposition. If you have two electric fields into the same space, the result or the resultant electric field is just the vector sum of all individual electric fields. Okay? So you could calculate two of them, add them together. Maybe it's 3 and you add them together. Maybe it's 4 and you add them together. Maybe it's 5 and you add them together. Maybe it's infinitesimally few and you integrate them to add them together. That's what we'll do a little later. Right? So you could just add every single electric field together. We will learn next week, and by next week I mean Friday, why that's a terrible idea for complicated systems. But for 1 or 2 or 3 particles, yeah, you can do that. You can just take the electric fields, which is Q over R squared, and add them all together. Now, we could rederive the electric field here again, right? We could go, okay, well, this is E is equal to Q over R squared, and we can go, well, this is E equals Q over R squared, but we're skipping it for time, so don't sweat this one. Question, Bestie?
It's R squared with respect to the point charge.
Yes. So I should say, you're right, we should call this R1, and we should say R1 squared. And we'll call this R2, and we'll say R2. You're very correct. And this kind of rigor is important. And, of course, in your exams, every diagram is way better than my bullshit diagrams. All right? You do not need to worry. There is no ambiguity in questions. There is only ambiguity in my life. Okay. So I have one more concept that we have to address. And I promise you, as the weeks go on, it's less 50 trillion concepts and more one concept that involves maths, okay? But to start off with, we have to just, learn 50 trillion different things. You remember polarization? What did you call it earlier? Dipole, right? What was your name? Tariq? All right, and Tariq's exactly correct. We could refer to this sort of thing as a dipole, right? Because it's got 2 poles, right? I want you to ask, is there an electric field due to this dipole? Well, yeah, there has to be, right? But first things first, if you were 10 trillion light years away from that dipole, those 2 charges are basically on top of each other. It's functionally 0. If you could treat them as a point charge, as an point charge, not 2 point charges. If you could treat them as 1 point charge because you are so far away, the electric field will be 0. And what this tells us is that whatever expression we have for the electric field has to have a dramatic drop-off with distance. Because we know if you are zoomed out, it should look like a neutral charge, should look like no charge, right? If you are so far away, those two objects are basically on top of each other. But of course, when you're in its proximity, as long as you're not too far away from it, they do have an electric field, and it is assessed. So we could derive it. Let me check if we do derive it. We could. Will we? No. Of course not. We could derive it. But what I'm going to do first is show you the ideal dipole. Okay? Dipoles are by definition the same magnitude of charge on both sides. It's Q. They are by definition separated by a distance d. And typically, we are concerned with the electric field along the axis of their separation. We could do other ones, but it's functionally uninteresting. So we typically care about the electric field along the distance of their separation. Now what you could do is at any point R, you could find the electric field due to this charge, and you could find the electric field due to the other charge, and you can add them together for every single point. And believe me, I did practice the derivation so I could show it to you. But you do not need to know it, and therefore we will not do it in concession to time. Okay? Instead, we are going to first define, and we've got 3 slides left, so don't worry, we're almost done. I know, I'm tired too, bestie. I want to snooze, right? We have, that's a joke. I'm so alive right now. We are first going to define something called the dipole moment. And every time I do something in my house, I'm thinking to myself, that's a certified dipole moment, right? It's like, I'm trying to think, do you guys know, have you done any other moments before? Like moment of inertia, I guess? Anyway, it's a quantity that's also direction-y, if that makes sense. A dipole moment is a vector, because dipoles have an orientation, right? So it has to be a vector, because the direction matters. The magnitude of that vector is Q times D. Q being the charge. Now remember, one of them is plus Q, one of them is minus Q. So Q is the charge. It's not half, right? One of them is plus Q, one of them is minus Q. Q is the charge. D is the distance, okay? The distance they're separated. So the more separated they are, the more dipole-y they are, right? And that should make sense because the further apart the two charges are, the more unlike a single charge they are. The more on top of each other they are. Question, Tarek?
Why is the direction in the space of time from negative to positive?
Because of the relationship to electric field that I'll show you in just a moment, actually. We have to pick a direction. It has to be either the way I've drawn it or the other way. Those are the only 2 obvious choices. And we had to pick one. And I didn't do anything, right? Old physicists did this. It was chosen so that it points from the negative charge to the positive charge because that is the direction of the electric field that it exudes. This positive charge here, if you were to calculate the electric field at this point, it would be mostly to the left because the positive charge is closer to this side. So the electric field would be more, that's left, right? This electric field would be stronger than this electric field at the point on the far left. At the point on the far right, the electric field is mostly, again to the left, but mostly attracted into the negative dipole. And so this direction, defining it as pointing from the negative to the positive, means that our definition of electric field has just the direction of P in it, right? The direction of the electric field due to a dipole is equal to 1 over 2 pi epsilon naught. Don't be caught sleeping. 1 over 2 pi epsilon naught. P, the dipole moment, divided by r cubed. Remember we said that it had to drop off dramatically with distance. So it's 1 on r cubed. instead of 1r squared. Now, if our dipole moment was defined the opposite way, if we defined it as pointing from the positive to the negative, then we would have to put a negative sign in here, right? That's the only difference that would make. So we just made a choice, right? And again, this is along the axis only. If you want to do any other point, well, then you have to do it by hand, right? If you wanted to find the electric field here, then you have to find the electric field due to this charge, and you have to find the electric field due to that charge, and you have to add them together yourself, right? But this way, along the axis, we get to use this formula. Now, this assumes that the distance you are away is much, much greater than d, okay? And we will look at, next week, relaxing that assumption. But for now, this is the assumption that we have. Now, I'm showing you this only because it shows up in assessments, right? That's the dipole moment. I think that is my only slide. That is my last slide. So I'm going to close on just asking, why, right? An electric dipole is a quantity that is actually very useful because any object, right? Let's say, for example, a water molecule, right? A water molecule is charge neutral, has no net charge, but it still does electrical shit. And the reason it does electrical shit is because it's polarized. It's got a positive end and it's got a negative end. That's why microwave, the cooking thing, works, right? And so we can treat water as though it is a dipole. And I forget which end is the positive end, so forgive me, right? But we can treat water as though it's a dipole and do a lot of maths on it, which is why dipole maths matters, is because you can take objects, like there are a lot more dipoles out there than there are charges, right? Because a lot of objects are dipolar. Anyway, that's the whole lecture. Thank you so much for paying attention. Next lesson is on